Okay, so let's talk about the midterm. So it's going to be next week on Wednesday. What day is that? Wednesday, April 22. Okay. And we're going to do it live. So, and I'm going to have 2 exams. Okay. So, if you're here right now, I'm assuming, so it'll be quote unquote live. All right. 2 exams. Okay. One from 10 a.m. to 11:10 a.m. Okay. One exam, and then and if you are in a super far time zone, I'll have another exam from 10 p.m. to 11:10 p.m. This is all California time. So, whatever 10 p.m. you got to figure this out yourself, or whichever one, all right? And it will be live proctored via Zoom. Okay, so I'm gonna have everyone log into Zoom, turn on their webcams, webcams on, mics muted, and we'll do that. Okay, it's going to be a pen and paper exam. And via Gradescope. So I've been kind of checking out a few options. And so the way it's going to work is on Gradescope, I upload a PDF, okay? PDF of the exam. And that will become available when the exam starts. And what I've done is I've created a practice 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 test with GradeCamp, okay? And I will unlock this, and you can take a look at it. But basically, you can try practicing it, okay? And so and the way it's going to work is there's going to be a few problems. I think what I'm anticipating is like 5 problems. Okay. Okay. Practice test with GradeCam. Okay. There's going to be 5 problems, and you will need 5 sheets of paper. Each problem is on 1 page, and that's it. Okay. And so the way it's going to work is so for the practice one, I think it's created a practice test. The practice test is two problems, 2 pages. Okay, and the way it's going to work is you're going to so you can choose to print out the PDF. I mean, that might use up a couple minutes, and you need to have a printer for that, but you don't need one. Okay, you can just start off. So what you can do is you can print out the PDF, and it will be 1 problem per page, and then you answer your thing, and then what you do is you got to scan it and upload it back to Gradescope. Okay. The other option is you don't print it out. You just start off with 5 blank sheets of paper. You just label each page with your name and problem 1, and then after you finish, you write all of your work clearly on the paper, and then you scan it. Okay, so each problem is 1 page, and then you will need to quote unquote scan the exam and upload a PDF back to Gradescope. All right, and so you'll I'll post a practice test on CCLE that you can kind of try and practice and clearly do it before Wednesday. Okay, so you have between now and Tuesday to just kind of practice how to use Gradescope. Okay, for scanning apps, if you have an Android phone, I'm a big fan of Google Drive. Google Drive has a built-in scanning app. If you have an Apple iPhone, there's like the Notes app where you can things. Can you use an iPad to write on it? Huh. I guess. Will it make PDFs and stuff? I guess if you can handwrite your answers on an iPad and stuff, yeah, that's fine. We'll try it out. Try it out, okay? Try it out with the practice Gradescope. That's the purpose of this practice Gradescope test, okay? So try it out, see if you can make a PDF and upload it back to Gradescope, and I hope you know what? I better make it. I better change the Gradescope practice to like Monday, and that way. Okay, so just give me a second. What you can't write on both sides, okay? It's got to just be one side. Everything has to fit on the front side of one paper, okay? Because I've configured the Gradescope, so I just told it one problem per page. I'm telling it that, and so that's what it's going to expect, okay? So yeah, okay, so that's what I'm going to do. So for the practice test, I'm going to make the practice test close on Monday, and then that way on Tuesday I can like go through and like practice grading it, and then if something is wrong, like I can't read your iPad PDF or something, then I'll let you know. Okay, so so I'll make it do. So what is this? I created a practice test with GradeCam. Finish by Monday. Okay. Practice is 2 problems, 2 pages. Each problem is 1 page. You will scan the exam and upload back to Gradescope. You can use a quote phone, camera scanner app like Google Drive for Android, or what is it? Just the Notes for iPhone. Okay. I think there's other apps. There's like Microsoft Office Lens. I think there's like Cam Scanner and more. Okay. Exam is open note, open book. Yeah, I figure on a take home, not a take home, but like an exam that you're going to do. This is how it's going to work. Okay, and so the exam, I've written it for like 45, 50 minutes. Okay, but I'm giving you guys an hour and 10, so you can scan it and upload it. Okay, I'm giving you extra time for the kind of the scanning and uploading portion. So you've got to kind of pace yourself. Make sure you have at least, I would say at least 10 minutes to take care of the scanning and uploading. Okay, if you don't have it uploaded by 11:10, you're gonna get in trouble. Okay. I'm assuming this is okay. Yeah. Should you print out? No, you don't need to print out the lecture slides. Okay. There's like a bajillion slides, so you can use the computer. All right, the computer's there. Yeah, that's fine. Okay. Will it be more difficult than a normal exam since this is open notes exam? I don't even know how hard the normal exam is in the first place. So I tried to make an exam of appropriate difficulty. Obviously I've got to test stuff like your understanding. So it's not just like you scroll through the notes and you just copy an answer from notes, right? Like I've got to do something a little bit more than that. So so it's going to be harder than just find the answer in the notes and copy the answer down. Okay, and I'm going to tell you, like, I think I'm being nice. I'm going to tell you kind of what kind of questions you can expect. Okay. Some of you have testing accommodations, and I think the way that works, if you get like extended time, is basically I just change the deadline, and I think that's how it works for you. I'll have to double check. Okay, are there any questions just on the format of how Gradescope and this is going to work? Okay, this seems okay so far. Okay, and again, yeah, make sure you try out the practice thing, okay, so you can see how it works. Okay, all right. We have to write out any code by hand. Yes, so this, no code. I don't think. Let me, yeah. I'll tell you the problems, okay? I'll tell you the problems. I have to type. I'm gonna type as I talk here, okay? The first one's gonna be dealing with vector derivatives. I'm gonna give you some kind of function, okay? And that in vector notation, in vector form, some kind of function in vector notation. And you're gonna find the gradient of that function with respect to a vector, all right? And so for practice, you can look at like the OLS loss function in gradient in vector notation or in vector form, and you can see how I took the gradient or the derivative of the loss function with respect to W. Okay, on the test, all right, the problem is not going to be the OLS loss function because that's straight from the notes. It's probably going to be a tiny bit more complex. So you'll have to work through that, okay? And but that's that, okay? So that should be, I think, okay. All right. Next problem, second problem that I've got planned is gradient descent, okay? I'm going to provide a function in 2 dimensions. And I'm going to provide an arbitrary starting point, okay? And then and I provide an arbitrary learning rate gamma, okay? And then what you're going to do is you are going to you will calculate manually the location at so starting point. So this will be time at t equals 0, and then you'll manually calculate the location at time t equals 1 and t equals 2. Okay, so applying the gradient descent algorithm, right? So this is what you have to do. So that's going to be kind of a little bit of manual work there. I'm going to ask questions about regularized loss. Yes, can you use a calculator? Of course, you will definitely need a calculator, okay? So for the exam, you need sheets of paper, a pen, and a calculator. And you can have notes and stuff and your textbook and all of that, okay? All right, regularized loss, okay? So I will provide a small data set, like 3 or 4 points in 2D. And then I will provide a fit line. Okay. Does it have to be pen or can we use pencil? Yeah, you can use either pen or pencil, that's fine, as long as it scans and I can see it, right? So You know, if you write really light with a pencil and you try to scan it, like there's a possibility that it doesn't show, okay? And then that's gonna be a problem. But as long as I can see it, right? Because all I'm getting is the PDFs that you scan. So you know, please, when you use like a camera scanner on your phone, like if some of you actually have a real scanner, okay? If you haven't got a real scanner, great, okay? But if you don't, which I imagine most of you don't, you'll need some kind of app to scan it using the thing. You know, please take like a couple moments. Some of them have like automatic cropping. You know, whatever you can do to kind of crop your the image so that it's focused on your on the portion that's going to be helpful. Okay. Regularized loss. So I will provide a small data set, like 3 or 4 points in 2D. I will provide a line of, I guess I'll provide the equation for a fit line, okay? May or may not be necessarily be a great line, okay? Okay, for a potential, all right, potential fit line. Line of fit, I don't know, whatever we want to call it, okay? And then what you are going to do is you will find the OLS loss, and then you will find the lasso loss. Okay, I'll provide the lambda value. And you will find the ridge regression loss. I'll just call this ridge loss, okay? Lambda value. Okay. All right, so that should be easy. That should be easy, really easy. It's a matter of finding the OLS loss correctly. Okay, and then you'll have a kind of manual leave one out, cross-validation. And what I'm going to have is I'll have a small data set, again, 3 or 4 points in 2 dimensions, okay? And I will provide the equations for 2 competing two competing models, okay? And basically, you will have to, you will perform, leave one out, cross-validation for each model, okay? And you're gonna find the, so I'll provide the equations for 2 competing models. So I guess, so what this will look like is, I will go ahead, I will provide lines fit to n-1 points, okay? And each model will have, you know, n different fit lines, okay? And you will find the mean cross-validation error for the competing models. So okay, so I should say I will provide, this is probably better stated this way, okay? And I'll post this document, okay? So I provide a small data set, 3 or 4 points in 2D, and I'll provide kind of 2 competing models. And what you're gonna do is you're gonna perform leave one out, cross-validation for each model. And so I will go ahead and I'll provide the fit to the lines fit to n minus 1. And so each of these will have kind of n different fit lines, and you're going to provide the mean cross-validation error for the competing models. So you have a problem like this in the homework. It's very similar to the homework, except the computer's doing it. I would recommend just trying it out with like really a small data set. Like you can kind of reform. It's similar to the homework, except you're going to be doing it manually with a much smaller data set, and all the calculations are your own. Okay, and then the last one will be some conceptual questions. Kind of covering material from lecture. I don't know how else to say it. Okay, covering material from lecture. You know, some of the answers will be directly in the notes. Some of the answers, you know, you might have to think a little bit about. Okay, some answers can be taken directly from the notes, and then some answers will require a little bit of thinking. Okay. And, you know, we'll have a small handful of those, okay? Okay, any questions here? Does this feel okay? So let me save this document. Save to. We'll save it there. Okay, then I'll post this. What's going on? All right, are we going to have to do manual matrix algebra to find the nth lines of fit for leave one out cross-validation? No, I will provide the lines fit to the n minus 1 points, right? So if you've got like points 1, 2, 3, 4, I will tell you what the line looks like when it's fit to points 1, 2, 3. Okay, and what the line looks like when it's fit to points 1, 2, 4, what the line looks like when it's fit to points 1, 3, 4, and what the line looks like when it's fit to points 2, 3, 4. Okay. So you don't have to do like X transpose X inverse X transpose Y or something like that. No neural networks, okay? No neural networks on this one. That'll be, that's for the future. Okay, that took a lot of time. Let's go ahead and start today's lecture content then, and what's going on here? Okay. Okay, so today we'll continue our neural network topic, and that's what we got. All right, so we've got, okay, you know what, I'm gonna skip over this. So what are the dimensions of this? All right, and so what we covered on Wednesday, kind of forward feed, and we did the sigmoid activation function, and we said this is to go from your X to your Y hat. You take your X and you multiply it by your first weight matrix, right? You have your X, you multiply it by your first weight matrix, that gives you your Z's. You apply an activation function to the z's that gives you your a's. Then you multiply the a's with the second weight matrix, and that will give you your next set of z's, and you apply an activation function there, and you get y hats. Okay, and that's what we've got here. X times w gives you z. Apply the activation function to z, gives you a. Multiply a by times the second weight matrix, that gives you another set of z's. Apply a function to z's, and that gives you y hat, and that's what we have here. All right, so this is what we want to do. We want to train our neural network. We want to train our neural network, and training the neural network in this case means finding the values that go into W1 and W2 that will minimize the loss function. So our loss function can be written like this, or it can also be written in vector notation. And we have to just keep in mind that the predicted values are no longer as simple as they were in OLS regression. In OLS regression, it was just XW was our values, but now we've got f of XW1 times W2, okay? And so we want to figure out the derivative of this, okay? And so finding the derivative or the gradient with respect to the loss functions, that process is known as backpropagation, okay? And that will allow us to find the gradient, and in this case, once you find the gradient, the form of the gradient is too complex, where we can't just say, let's set the gradient equal to 0 and solve for W, and solve for W1 and solve for W2. It's too hard to do that. So we're going to find a gradient, and then we're going to do gradient descent. So we're going to start off at some arbitrary location. Now that we've got the gradient, we can take steps downhill. So we're going to use gradient descent, okay? Gradient descent is not guaranteed to converge. We saw when you have different learning rates, gradient descent can bounce all over the place. But if we have the correct learning rate, it can help us get towards a local min. All right, so here's our simple neural network. We've got two inputs, x1 and x2, and an output y, 3 values in the hidden layer, okay? And so the loss function, for whatever reason, the video from Welch Labs, they use J for the loss function, okay? Rather than L. So just to kind of fit that notation, I'm also gonna call it J, all right? And so the gradient of J, all right, that's just the loss function, with respect to W1, okay, is going to be a matrix with the same dimensions as W1, okay? So W1 was our first weight matrix, and that was a 2 by 3 matrix of W's, right? It's got 6 values. And so the gradient of a function with respect to a matrix or vector is always going to be another matrix or vector that has the same dimensions, okay? So here, the gradient of J with respect to W1 is also a 2 by 3 matrix. The gradient of J with respect to W2 is also going to be a 3 by 1 matrix, okay? Because W2, the second weight matrix, is 3 by 1, right? If we have bias terms, okay, you're going to have to find the gradient with respect to the first and second bias matrices, all right? And I'm not going to do that here. That's going to be part of your next homework assignment. Is you're going to have to find the gradients yourself. It's a bit of work, but it's good. Okay. All right. So what you're going to see on the next, I don't know, 30 slides is just a whole bunch of matrix. Just a whole bunch of derivative taking with respect to vectors and stuff, okay? So our loss function, okay? Our loss function is going to be the difference between the actual value y and the predicted value y hat, okay? That quantity squared summed up, and I just threw in an arbitrary constant of 1/2 just so that when I take the derivative of this, it'll cancel out, so I don't have to deal with the 2 the whole time, okay? So, so here's our loss function, right? So the derivative of this with respect to W2, derivative with respect to the sum is going to be the sum of the derivatives, and so this gets this. Then, the derivative of this, the 2 comes down, and then you take the chain rule, okay, and you say, okay, what changes with respect to W2? The only thing, so yn is a constant, right? This is a constant. It's a fixed value. It doesn't depend on the weight matrix 2, but y hat, our prediction, does depend on the weight matrix, okay? So I have to apply chain rule, and so we're going to get a -1 because we've got a minus y hat, and then I need the derivative of y hat with respect to W2, okay? All right, and then I say, okay, well, how does y hat change with respect to W2, okay? So because of chain rule, all right, we can say, well, y hat changes with respect to the value before it, which was the third z value, okay? So if we back up to right here, we said y hat is going to be the result of applying that sigmoid activation function to the z values in the third layer, right? So y hat changes with respect to this, and then z changes with respect to W2. So this is where we are, okay? And so each of these terms will have to we'll have to do some a little bit of calculus here to figure out how y hat changes with respect to that input value zn, z sub n, and then we'll have to ask how z sub n and changes with respect to the second weight matrix W. Okay. If any of these steps feel like, wait, how did you do that? Just raise your hand or give me some kind of feedback, and I'll pause. Okay, so I write, remember, y hat is the result of passing the value of z through the activation function. So the derivative of y hat with respect to z, okay, in that third layer, is just the derivative of the activation function. So if we say y hat is equal to f of z, z in the third layer, then dy d hat dz, okay, I'm sorry, dy hat dz is going to be f prime of z, right? So if this is our activation function, which is the sigmoid function, okay, 1 over 1 plus e to the negative t, then the derivative of this, right, using quotient rule, so remember quotient rule from back in calculus, right? So derivative of u over v is u prime v minus uv prime over v squared, okay? So we're going to let u equal to 1 and v equal to 1 plus e to the negative t, and anyway, you do all of this derivation, and you're going to get f prime equal to e to the negative t over 1 plus e to the negative t quantity squared, okay? So derivative of y hat with respect to z is going to be f prime of z, okay, which is equal to e to the negative z divided by 1 plus e to the negative z quantity squared, right? So you might need to go back to your, what is it, 31A notes to review derivatives if you've forgotten things like quotient rule and stuff like that. Okay, so anyway, this is what we've got. And just for simplicity, rather than having to copy and paste this and plug this in everywhere, I'm going to just leave it in the form f prime of z, okay, f prime of z. So so this is where we left off, okay? We said the derivative of this is going to be equal to the sum for all the n's of yn minus y hat n, and I've got dy hat dz, and we're going to just replace that with f prime, okay? And now I've got the derivative of Z with respect to the second weight matrix, W2. All right. So far, so good? Am I losing anybody? Great. Thanks for your enthusiastic feedback here. All right, so I hope this is okay. I'm gonna just click next here. Again, if any of this feels not good, just let me know. All right. So this is where stuff gets a little bit maybe a little unusual. Okay, so everything, you know, we've just been dealing with one particular instance. So far we've been dealing like with one value y sub n and one value y hat sub n and one value z sub n. Okay, we have to remember though that this z, there's a z matrix. Okay, and z matrix is an n by 1 matrix, right? Because we've got one node in that third output layer. Okay, so z3 is technically an n by 1 matrix, right? And it's the result of multiplying the A matrix, okay, the result, that second weight matrix, or second the values after activating the original z's times that second weight matrix. Okay, and so if you think, if we just focus on one value, right? So if we got z is n by 1, which is the result of n by 3 and a 3 by 1. Okay, let's just look at one value. So this is a scalar value, 1 by 1, and we look at what A is, which is a 1 by 3 matrix, and W is a 3 by 1 matrix. Okay, we can ask, well, what is the gradient of z sub n, just this one value, with respect to the W2 matrix? So what do you guys say? Right. So do you guys remember all the way back, was it lecture something in week 2 or week 1? I don't remember. One of the earlier lectures we had rules about taking derivatives or gradients. Okay, so the gradient of you know, some scalar value with respect to a matrix is going to be this thing, or with respect to a vector is going to be the thing that it's being multiplied by transpose, right? So so the derivative or the gradient of this, okay, is going to be a sub n transpose. Okay, so the A, okay, the A matrix, the full A matrix is n by 3, but if we just isolate one row is going to be a 1 by 3 kind of row matrix, and the gradient of that is going to be that row matrix transpose, which will be a 3 by 1 column matrix. Okay. So let's take a look at this, right? So I'm going to plug this in. So if we're still dealing with just one value at a time, okay, it's going to be the sum of y sub n minus y hat sub n f prime of zn. And if we think about this, these are all just 1 by 1 scalar values. Okay, so this is a 1 by 1. This is a you know, a scalar value. F prime of a scalar value is a scalar value. So this is a 1 by 1 scalar value. And then when we ask, well, what is the gradient of this? Okay, the gradient of this was that 3 by 1. So A sub n transpose is going to be a 3 by 1 matrix. Okay, and so when I multiply the scalar by this, I'm going to get a 3 by 1 matrix. Okay, and then what I want, okay, is I want to somehow get rid of this summation, right? So here I want to be able to kind of add all of these terms up. Okay, I want to add all of these terms up, because what should the dimensions of the loss function j with respect to W2 be? The result of this should have the same dimensions of W2, which is 3 by 1, okay? And if we just say, okay, well, what's the loss with respect to just one of these things? This works out to be a 3 by 1, okay? But what I want to do is I want to kind of turn everything, rather than having to sum them up for all of the n's, I want to somehow be able to do that using kind of our all of our n terms, okay? And so if I say, well, what if I just turn everything into its vector forms? Can I just do that, right? And get rid of the sums? Well, we're going to get this, right? We're going to get y is going to become y sub n will become the matrix y. Y hat sub n will become the matrix y hat. Okay, and that's it. Those are each n by 1, and I can subtract them. Okay, I can add or subtract them together because they're the same dimensions. Okay, z sub n, okay, is a unit value or a scalar value, and if I say, well, let's apply it to all z's, that's going to become an n by 1 matrix. Okay, so z, the matrix Z3 is n by 1, and this A transpose, okay, which is currently 3 by 1, when I expand it, okay, is going to be a 3 by n, okay, because A2 itself is an n by 3 matrix, okay, the A2 matrix is n by 3, but I'm taking the transpose, and this is 3 by n. Okay, so if I try to multiply this together, I'm going to get dimension mismatch, right? I can't do n by 1 times an n by 1, okay? And I can't do an n by 1 times a 3 by n. So what am I supposed to do, right? It seems like this is no good. This back here is okay. I've got scalars and a 3 by 1, and this will give me the correct dimensions here. But the result is I want to get basically a 3 by 1 here, okay? So what I'm going to do, all right, and this feels a little bit scary, but is that these are all the correct terms, but I kind of need to find the correct combination and way to multiply them. So what I'm going to do is I'm going to actually bring the A transpose to the front, okay? I'm going to bring the A transpose to the front, okay? And then I'm going to multiply this n by 1 matrix and this n by 1 matrix. I'm going to do element-wise multiplication, okay? I'm going to do element-wise multiplication. So this quantity here is y minus y hat, that's an n by 1 matrix. And here I've got f prime of the Z3 matrix, okay, which is also an n by 1 matrix. And I'm going to do element-wise multiplication, which means I'm going to take the first element and multiply by the first element. Second element times the second element, third element times the third element. And so this times this together, okay, is going to remain an n by 1 matrix. Is that okay? So, and if you watch the Welch Labs video, he calls this value delta 3, okay? Delta 3, it's just an arbitrary name, but this is going to be the product of this n by 1 matrix and this n by 1 matrix element-wise, okay? And that's what this symbol represents. So it's not regular old matrix multiplication. Regular old matrix multiplication would require us to kind of transpose one or the other. We're not going to do that, okay? We're going to go element-wise, and so this is going to be an n by 1 matrix. And when I take this and I have A transpose, which is 3 by n, multiplied by this, which is n by 1, okay? 3 by n multiplied by this quantity, which is n by 1, that's going to result in a 3 by 1 matrix, which is exactly what I want, okay? I want that, the derivative of the loss with respect to the second weight matrix will be a 3 by 1 matrix, okay? Where this quantity is this thing. Okay, because we want the gradients to have the same dimensions as W2. W2 is a 3 by 1 matrix, so we want the gradient of this to also be a 3 by 1 matrix, and that way I can kind of add on the gradient to the original value here in gradient descent. Okay. Did I lose anybody along the way? Are we okay? with this? I feel like I know it's a lot here, but I wrote all the dimensions underneath each of these terms and elements, and I'm hoping that will be clear enough for you to be able to follow along. Okay. Oh, quiz answers. I haven't given out the quiz answers. You are right. I totally forgot about that. What is today? Today is Friday. Losing track of time. Friday. First quiz answer is A as an apple. A as an apple. And second quiz answer, D as in dog. Okay? Apple and then dog. A as in apple, D as in dog. That will be today's. Oh, no. Shoot. Scratch that. Okay, nobody, I read the wrong table. Okay, it's A as in apple, E as in elephant. I apologize. A as in apple, E as in elephant. So did anyone already answer the quiz? A as in apple, E as in elephant. I apologize. I read the wrong table. A as in apple, E as in elephant. A, E for today's quiz answers. A followed by E. Okay. So we'll go from there. Okay. And then, okay, you already answered. All right. I'll fix it for the couple of you who answered already. But A and then E for the quiz questions. Okay. Oh, we're out of time. Okay. So the other one is we've got to find the gradient with respect to the first weight matrix. Maybe we can I can have you start looking at some of this. I guess I'll just continue these slides. Okay, so on Monday when we get to this, I'll just finish off the rest of these slides here. Okay, and you can start. You can kind of take some time if you want to go ahead and start looking through this, and we'll end there for today. Okay, so so on Monday we'll pick up on slide. I forgot. Oh, shoot, where is it? Second weight matrix. We need. Yeah, we'll pick up for the with respect to the first weight matrix. So this slide 24 here. Okay. All right. We'll end there, and so have a good weekend, and we'll see you guys on Monday, and we'll finish the rest of back propagation. We'll code it up, and we'll take a look at neural networks and gradient descent. Okay.